right, this is where the statistical magic starts. Let's talk about the Central Limits Theorem. And we'll look at an example in R. All right, the Central Limits Theorem is what allows us to connect estimates we derive from our sample back to predictions about our population. So let's say that we want to predict, or we want to learn something about the heights of students on campus, and we have 20,000 students, and we interview 500 of them, and we ask them their height. Okay, so we have an N here of 500 because we've talked to 500 people, and over here we have a capital N of I don't know how many students we have, 24,000 students. Okay, and we want to be able to tie our sample back to our mean somehow. How can we make a connection between these predictions? And we can't do it directly. We have to rely first on the Central Limits Theorem, which then allows us to make predictions about the population. And here's how that Central Limits Theorem works. It has three main ideas. It is that the sample mean, well, let me be more specific here. We have three mathematical facts that we know about the Central Limits Theorem. Anytime we predict something about our sample, so here we're making a prediction, or we're making an estimate about the population mean. Okay, so we're making a guess. This Central Limits Theorem deals with that guess. So this guess will have the following characteristics. First, it will belong to a normal distribution. Now, I am not saying that the original sample will be normal. It may not be. But the mean that we are estimating will belong to a normal distribution, a theoretical normal distribution that exists out in statistical space. Not only will it belong to a normal distribution, but the sample mean will be essentially equal to the population mean. So, well, not necessarily to our population mean, but to the mean of this distribution. Okay, so our sample mean from our sample will be the mean of this theoretical normal distribution. Okay, and the third idea is that the standard deviation of this unknown, well, not unknown, but this uncollected, this theoretical normal distribution will be equal to the standard deviation of our sample divided by the square root of the sample size. Okay, so because of these three ideas, we have not just this mean, but we have a normal distribution of means related to that data, and our mean that we have calculated here is the mean of this theoretical distribution. And the standard deviation of this distribution can be predicted using the standard deviation of the sample divided by the square root of n. And where this gets useful, why this is such a cool idea, is I can report the mean. And what I'm going to say over here is, let's say that I took the mean height, and it's, we'll keep it simple, it's 5 feet 5 inches, right? This is our mean. So we can assume that because this is the mean of our sample, it's also the mean of our population. But how confident are we? How confident are we that those means line up? Well, we can come back to this theoretical normal distribution based on our Central Limits Theorem and say, well, here's the mean. If you want me to be 95% confident, let me move out away from that mean in both directions until I have encompassed 95% of that curve. This range, then, is our 95% confidence interval. So we can report not just that the mean is probably close to 5 feet 5 inches, we can say we are 95% confident that it's plus or minus 4 inches. Okay, so that our confidence interval then is we are 95% confident that the population mean is not less than 5 foot 1 inch, nor is it greater than 5 foot 9 inches. So we have created our confidence interval, which is realistically just the interval of the theoretical normal distribution. Let's take a look at that in R. I've already typed out all the R script, but let's just go through what we're doing here. Here I'm cleaning off my workspace to make sure that I do not have any lingering values from some previous analysis that may confuse me now at this point. I am opening up the volcano data set, which is an elevation data set of a volcano in New Zealand. I think if I remember right, the maximum, just to give you some idea of what the data look like, it ranges from 94 meters above sea level to 195 meters above sea level. So we have a data set with this data is a matrix. So we have over 5,000 elevation samples scattered uniformly across the volcano. Okay, so here's what we're doing. Let's create our actual sample here. And what I'm doing, I'm setting the seed to 12, which sets my random number generator, which is used in the sample function. It tells it to begin at 12. And I normally would not do that. In a real analysis, I would never do that. But in this case, I'm setting the seed so that if you're following along in R, you can get the same answers that I get and know that you haven't made any mistakes. So here I am telling the random number generator to be a little bit less random so that we all get the same result. I'm using the sample function where I'm going to randomly sample 100 values from the volcano data set. So when we run this, I now have an object called mySample, which contains 100 randomly selected values from the volcano elevation data set. And from that, I'm going to calculate the mean, the standard deviation, and the sample size of that sample. Okay. So normally this is what we do. This is where we would stop. But because I want to demonstrate what is happening theoretically out there in statistical magical space, here's what we're going to do. Normally, we just have one single guess for our population mean. We've calculated our sample mean here as 131 meters. And so we would say that our population mean, the average elevation of this volcano is 131 meters. But let's say for just a minute that we're going to go through the whole process of verifying the central limits theorem. So in this case, I am randomly sampling 5,000 values, and I am creating 50 samples with a sample size of 100. So this is, and then I'm finding the means of each one of those samples. So the theoretical, when I run it, I'm calling it the theoretical just to emphasize the fact that it is a theoretical distribution that normally does not exist, but we're calculating it here so that we can show you how that works. So we have a theoretical distribution of guesses about this volcano's mean. So this is a theoretical distribution of guesses. Here we have one single guess that we have based from our sample, and this is how we normally do science. But to illustrate the point, here is our theoretical distribution of guesses about the mean. Okay, it's just a coincidence in this example that our guesses were guessing about the mean, but that's what we have here. Okay, so the first idea of the central limits theorem is that this theoretical distribution of guesses will be normally distributed, whether the original data are or not. So let's take a look at this. I'll make this line a little bit thicker so that we can see it. But here is our distribution of our guesses, and it is primarily a normal distribution. We have one sample here that seems to have, we somehow accidentally, in one of our 50 samples, we accidentally had one sample that happened to randomly grab 100 points that were a little bit higher than the mean, so we do have one oddity here. But our data are normally distributed, and in fact, we can submit it to a Shapiro-Wilks test, and these are normally distributed data. Okay, so we have the theoretical distribution of guesses is normal, just as the central limits theorem posits. The second idea is that the mean of the theoretical distribution of guesses will be essentially equal to the sample mean. So here is the mean of our theoretical distribution of guesses, 129.9, or essentially 130, and the actual mean from our sample is 131. So they are very close to each other, right? We can use the estimate of our sample mean as the mean of the theoretical distribution of guesses. Okay. Idea 3 is that the standard deviation of the theoretical distribution of guesses is going to be essentially equal to the sample standard deviation divided by the square root of the sample size. So here is the standard deviation of our theoretical distribution, 2.667, And the standard deviation of our sample divided by the square root of n gives us 2.359. Okay, so they're very, very close to each other. So this means that we can calculate the confidence interval of our guesses. So let me show you how we would do that, right? We have to calculate a z-score. And we can use a normal distribution here, but typically we end up using a t-distribution just because, as we've talked about, a t-distribution is the same thing as a normal distribution. It just accounts for smaller sample sizes. So our z-score here is going to be equal to, let's say that we want to be 95% confident. Okay, so for a 95% confidence interval, for the way that R is written, we need to make that 0.975. So that 95% confidence means that we have 2.5% of values in the tails. So we are looking for, it is the 97.5 quartile that separates that 25th, that 2.5% in the tails, right? So n minus 1. And so we are saying that 95% of guesses about the volcano height will fall within 1.98 standard deviations of the mean of our sample. Okay, so let me say that again. We are saying that we are 95% confident that the actual volcano mean elevation falls within 1.98 standard deviations of our sample mean of the elevations. So that gets a little bit tricky because we're talking about means in meters and then we're comparing it to standard deviations. So we convert the z-score back into units of, in this case, elevation, meters, by taking the standard deviation of the sample, dividing it by the square root of n, and multiplying it by z. So we're reversing the equation for a z-score, right? And so now we're saying 4.6, 4.7. So our population, or our sample mean, was 1.31. But we are 95% confident that the population mean is within 131 meters plus or minus 5 meters. In other words, we're 95% confident that the total population mean of elevation is not less than, let me say this as a confidence interval, is not less than 127, and it is not greater than 136. Okay, so our sample mean elevation was 131. But because of the central limits theorem, when we start talking about the population, we can say our sample was 131, but the mean of our population is somewhere between, we're 95% confident that it is somewhere between 127 and 136. And that's because of the power of the central limits theorem. Okay, in a real scenario, we don't have to do any of this. This is just to demonstrate how the central limits theorem works. But here we have everything we need to calculate the confidence interval of a mean, because of the power of the central limits theorem.